Let's talk now about what we're going to call endpoint independence of limiting parallel rays. And it goes roughly like this. If ray AB is a ray and P and Q and D are points P in between Q and D, then ray PD is a limiting parallel to AB if and only if ray QD is a limiting parallel to AB. Here's your setup. Ray AB, segment PA, ray PD. This is a limiting parallel if and only if this is. So endpoint independence means it doesn't matter where you start the ray along this line. Wherever you start the ray along this line, it will be a limiting parallel to AB. We will prove this both ways. So let's assume first that PD is a limiting parallel to AB, and we will show that QD is a limiting parallel to AB. So how do we do that? Well, we do it by contradiction. We assume that there is some ray QE such that QE is parallel to AB. So let's assume that there is, for the sake of contradiction, there is some ray QE, and QE never intersects ray AB. Well, we know that the measure of angle APD is greater than the measure of angle AQD by the exterior angle theorem. Angle AQP, I'm sorry, triangle AQP is a triangle, angle APD is an exterior angle, so the measure of APD has to be bigger than the measure of AQD. So here's what we do. We make angle DPF such that angle DPF is congruent to angle DQE. So DQE is smaller than DQA, which is smaller than DPA. So we can take this smaller angle and copy it over there. DQE congruent to DPF. And if that's the case, then the two red rays are parallel by corresponding angle theorem. And if that's the case, then PF is parallel to QE. And if that's the case, then it cannot intersect AB. Right? Because A and B are on the opposite side of QE from P and F. So PF is parallel to QE, QE never intersects AB, P and A are on opposite sides of QE, so PF has to be parallel to AB, and that's a problem because ray PF is in the interior of angle APD. That's a contradiction. It is also true the other way. Reset the picture. Reset the picture. So let's go the other way. Let's assume that QD is the limiting parallel. We'll assume that QD is a limiting parallel, and we'll show that PD is a limiting parallel. So how do you show that PD is a limiting parallel? Well, you take some ray interior to angle APD, and you try to make it parallel to AB. Let's assume that PE is interior to angle APD and PE is parallel to AB. What goes wrong? Well, consider QE. I mean, Q is a point, E is a point, so ray QE exists. What does it do? If ray QE never intersects AB, ever, then QD is no longer a limiting parallel. But if ray QE has to intersect AB, then it has to cross PE again. And that's a problem. That's a serious, serious problem. So whether QE intersects AB or does not intersect AB, we reach contradictions. And so if QD is a limiting parallel, so is PD. So the big takeaway for you is that endpoint independence is a thing. It does not matter where you start the limiting parallel ray, you've got a limiting parallel ray. Okay? Okay. One other thing that I'll ask you to know but not prove. Your author lays it out. It's pretty big. If ray AB, ray CD, and ray EF are such that AB is a limiting parallel for CD and CD is a limiting parallel for EF, then either AB is a limiting parallel for EF or one of AB or EF is a subset of the other. You do get transitivity for limiting parallel rays, and that's an important thing for you to have. Okay? Okay. Great.